In this lesson, we're going to talk about how intermolecular forces affect properties, and this is our last lecture of the semester. So before we get to the properties, we need to know what happens if there's more than one intermolecular force acting on a molecule. Let's say it's like water. Water has London dispersion forces, dipole-dipole, and hydrogen bonding. If there are multiple intermolecular forces acting on a molecule, the strongest IMF determines its properties. So again, if we're looking at something like water, which has LDF, dipole-dipole, and hydrogen bonding, we would look at hydrogen bonding to determine properties. So the first property we're going to talk about is boiling point. So when a substance boils, which means we're going from liquid to gas. Like if we boil a pot of water, it's going from the liquid phase to the gas phase. What happens is we're going to break those intermolecular forces between those molecules, and the molecules get further apart. So we kind of talked about this in the last lecture. Let's say this is my beaker of water, and as a liquid, those molecules are pretty close together. If we were to put this on a hot plate and we were to boil it, as a gas, the molecules are much further apart. So remember, there are intermolecular forces holding these molecules together. So if we are separating those molecules, we have to break those intermolecular forces. So that leads us to our first trend. The stronger the intermolecular force, the more energy or heat needed to separate the molecules. So, the stronger the intermolecular force, the more heat we need to separate those molecules from close together as a liquid to far away as a gas. The stronger the intermolecular force, the higher the boiling point. Molecules with hydrogen bonding as their main intermolecular force would have a greater boiling point than elements that had dipole-dipole. Next property is called the heat of vaporization. Think of vaporization like becoming a vapor. Again, we're going from a liquid to a gas. Heat of vaporization is the amount of energy needed for a liquid to boil. Heat of vaporization is going to be the exact same trend as boiling. The boiling point is the temperature at which the substance boils. For example, water boils at 100 degrees Celsius. Heat of vaporization would be how much energy do we need to put in to get a certain amount of water to boil. So they're pretty much the same thing. Boiling point is the temperature. Heat of vaporization is the amount of energy. But it's both of them are describing liquids boiling. So they are going to have the same trend. The stronger the intermolecular force, the greater the boiling point. The stronger the IMF, the greater the heat of vaporization. The stronger the intermolecular force, the greater the heat of vaporization. Next, let's talk about evaporation. Let's say you spill a little bit of water on the table and you don't wipe it up. After a while, that water is going to evaporate. Again, going from liquid to a gas. The stronger the IMF, the slower the liquid will evaporate. Again, in order for something to evaporate, it's going from the liquid phase to the gas phase. Intermolecular forces are holding those molecules together. So if I need to break those intermolecular forces, if I need to separate those molecules, the stronger the force, the harder it's going to be to separate those molecules. The harder it is to separate them, the longer it's going to take to evaporate. Last property that we are going to talk about today cohesion or surface tension. Cohesion or surface tension is the resistance a liquid has to increase its surface area. Or a way to think of this is it's resisting spreading out. It is the resistance to spread out. Something that is very cohesive is not going to spread out. Again, think about water. Like if you've seen a drop of water or dew in the morning on like a blade of grass, think about how that water kind of bubbles up. It's not spreading out. That means it has a high cohesion. The stronger the intermolecular force, the greater the surface tension. So it's not going to spread out as much if it has a high intermolecular force. Again, intermolecular forces are going to hold those molecules together. If you have a really strong intermolecular force, those molecules aren't going to spread out, so they're going to have a greater surface tension. All right, so last thing for today is let's look at a few examples. And let's rank the following in order of increasing boiling point. So let's say I had water. Let's say I had methane. Let's do propane. And then let's do dimethyl ether. And ethanol. So the first thing that we want to do is go through and figure out if they are polar, nonpolar, and then figure out the strongest intermolecular force acting on them. So A, water is polar, and I have hydrogen bonded directly to oxygen. So this one would be hydrogen bonding. Remember, for hydrogen bonding, we have to have hydrogen bonded to a small electronegative atom. We're looking for oxygen, nitrogen, or fluorine. B, this one is completely symmetrical. All of our vectors are going to cancel out. It is also a hydrocarbon. It is only made up of hydrogen and carbon. That means it is nonpolar. Nonpolar molecules only have LDF. Same thing with C. This is a hydrocarbon. It is only made up of hydrogens and carbons. That makes it nonpolar. The only intermolecular force acting on nonpolar molecules would be LDF. D, this one would be polar. Oxygen is more electronegative. I am going to have a dipole moment, but I do not have any hydrogen bonding. Hydrogens are attached to carbons. So everything has LDF. Since this one is polar, it also has dipole-dipole interactions. Last one. I see a site of hydrogen bonding. Hydrogen is directly attached to oxygen. So hydrogen bonding. So now if we are going to rank these from the lowest boiling point to the greatest boiling point. Remember, we said that the stronger the intermolecular force, the greater the boiling point. The stronger that force holding the molecules together, the more heat energy we're going to need to separate those molecules. So we are ranking these from weakest to strongest. LDF is the weakest intermolecular force. I have two compounds with LDF. Remember, if you have two compounds with the same intermolecular force, they both have dispersion forces, then it goes by size. Propane has more electrons. We have more chances for those momentary dipoles. C is going to be stronger than B. So my weakest would be B, methane. C is slightly stronger because it has more electrons, it's larger, so slightly stronger. After LDF would be dipole-dipole. So I have A and E left. This one is a little bit tricky. E is actually going to be lower than A. The reason that A is stronger is because we have more sites of hydrogen bonding. Water has 2 sites of hydrogen bonding, which makes that stronger than ethanol, which only has 1. If we were to go through, I'll give you guys some actual numbers. This first one, methane, its boiling point would be a negative 161.5 degrees Celsius. Propane, a little bit higher, negative 43.6 degrees Celsius. Next would be my dimethyl ether, negative 11.2 degrees Celsius. Comparing my two hydrogen bondings, ethanol, positive 78.2 degrees Celsius, and water boils at 100 degrees Celsius. So when we're comparing LDF, we look at size. When we're comparing hydrogen bonding, the more hydrogen bonding sites you have, the stronger it is going to be.